Okay, all right. So we have Cindy on, and she's here to talk about promises and limitations, free energy methods, and drug discovery project. My God, my free energy promises a lot. Okay.
Thank you. Hello, it's my great pleasure to be here to present some of the real-world application of free energy method in drug discovery. I want to thank the organizers for putting this meeting together after 3 years of hiatus and inviting me for this presentation today. I have to say I'm under a lot of pressure after a lot of great talks, especially standing between you and lunch, so I try to be short. So binding free energy calculations have been widely used in drug discovery to advance hit to lead as well as lead optimization. So I want to cite this well-known example from Professor Schurz that even a relatively moderate prediction accuracy of about 2 kcal per mole error using a free energy method can improve the predicted, accelerate compound optimization progress by threefold a threefold reduction of time to achieve the tenfold improvement in binding affinity. And thermodynamically rigorous free energy methods such as FEP, thermodynamic integration, and lambda dynamics has really accelerated the binding affinity prediction and improved the accuracy. And these methods utilize some alchemical transformation process from one compound to a similar ligand through some intermediate states. But despite the accuracy, the most rigorous free energy methods are still have some limitation in application in the industry due to the time constraint as well as resource and availability issues. At the same time, the endpoint binding affinity methods have also provide a compromise between the speed and accuracy of free energy calculations. So these endpoint methods only take into account of the bind state and unbound state of the ligand, and it estimates the binding affinity based on the salvation free energy estimated from a Boltzmann electrostatic term, as well as a nonpolar term based on accessible surface area. So previous studies have shown that these endpoint free energy method can also achieve reasonable accuracy, especially for large-scale virtual screening. So in the first part of this presentation, I'm going to highlight a large-scale retrospective benchmark study at Merck to assess the variety of different free energy methods and share some key learnings. And in the second half, I'll demonstrate a prospective application of FEP on real-world drug discovery program and discover some caveat in the application. A few years ago, a bunch of free energy enthusiasts at Merck started a working group to assess a variety of free energy methods and try to develop best practices to deploy to the whole organization. So we leveraged both internal and external software and workflows, and including FEP+, GBSA, order map, shift key, and some empirical scoring functions for this retrospective evaluation. The entire data set consists of about 400 small molecule inhibitors across several therapeutic areas with varying level of protein ligand binding pocket complexity. And the data sets consist of 5 internal targets and 8 published targets from the Schrödinger FEP benchmark study. we aim to identify some use cases for different methods in hit identification, hit to lead and lead optimization stages of drug discovery. So in this benchmark study, the predicted binding affinity from Schrodinger's FEP plus demonstrated the highest and most consistent accuracy as compared with other methods tested. We attributed this to the high accuracy in the open LS force field with custom torsion parameterization, the use of explicit solvent, as well as the enhanced sampling adopted for both solute and solvent. So the free energy predictions from 7 out of these 13 systems achieved strong correlation with experimental values, and the RMSE and MAE are consistent with the published benchmark studies. It is found that 75% of these ligands have achieved predicted absolute error within 1 kcal per mole of experimental values. And the reliable performance across a diverse protein binding site and different properties and sizes of ligand demonstrate the physical rigorousness of the FEP in real-world applications. So while FEP have seen significant speed enhancement by acceleration of GPU card development and cloud computing resource, there are still some limited use in the industry due to scalability and availability. So it is important to test some alternative methods for compound prioritization, especially for large libraries. So in one evaluation, we tested 2 GBSA workflows, one from the Schrodinger prime, the other used OpenMM as the simulation engine and Ember force field. So as shown here, the binding free energy predicted from GBSA calculation has much lower numerical accuracy compared with FEP. However, the predictions from 9 out of the 13 data sets shown moderate to somewhat strong correlation with experimental values, especially for large data sets, for example, target 8, MCL1, P38 alpha, and PDE10. And additional analyses also found that some of these targets have higher correlation between experimental measured activity and log P or molecular weight. And this showed that GBSA calculations are better at characterizing those non-polar, non-specific interaction-driven pockets with relative pocket rigidity. In addition, there are some targets that didn't work quite as well. For example, base, CDK2, and TRK-A, and these targets usually features important crystallographic water network that bridge the protein-ligand interaction, as well as torsional barriers in protein side chain and ligand movement that are important in binding. So here is a comparison of like a compromise between FEP, the most rigorous FEP using optimal mapping, versus a simpler version of perturbation mapping scheme called star map. Basically, you identify a reference compound and connect like other ligands to this reference compound to perform the perturbation. And in this example, the PDE-10A dataset is a large dataset from many iterations of parallel synthesis, and we are able to generate a large activity range of compounds, which leads to a suitable dataset for evaluation. So using the optimal mapping FEP plus calculation, we identified the high accuracy with this method with RMSE of about a little bit over 1 kcal per mole. However, for such large system of more than 60 compounds, the FEP calculation took about 400 GPU hours on a Tesla V100 machine. When we tested running FEP using the star mapping scheme, the calculation cut the time required to compute the free energy of each ligand roughly by half, and there's not much difference in the free energy accuracy. So it's a reasonable kind of a middle way between the most rigorous FEP versus the cheaper methods such as GBSA. And we found only 3 compounds have absolute errors beyond 2 kcal per mole, and close inspection of these perturbation edges revealed that these are often associated with large structure changes or like conformational differences among ligands. For example, from 9S to S9UU ligand pair, by simply adding a methyl group, there's substantial change in the torsional preference of this amino pyrimidine torsion that leads to poor kind of conformational space overlap between the 2 ligands. In addition, prioritization of compound is the it has key importance in drug discovery. While these quantitative prediction accuracy is important, it's also is not always necessary for decision making, because often designs are prioritized based on the top percentage of designs that included in the free energy evaluation. So in this case, we try to utilize a slightly different statistical metric to evaluate the performance of free energy methods. We utilize a hypergeometric test to compare the enrichment power of the top 30% of compounds among different methods. And the p-value determined from this hypergeometric test is commonly used in biostatistics to measure against the null hypotheses that the probability of observed enrichment is due to randomness compared to other enrichment matrices such as enrichment factor or like bedrock scores, for example. Because the p-values is less dependent on the size of the data set or some intrinsic hyperparameters. So here we computed the logarithm of the p-values for each binding affinity method. And a p-value lower than -1.3 indicate significant enrichment at more than 95% confidence level. So relative FEP calculations achieve still very superior accuracy and most consistent performance. However, some of the computationally more cost-effective methods, such as GBSA, also achieve reasonable enrichment capability that make them a suitable tool for prioritization or the selection of a subset of designed compound for more rigorous FEP calculations or free energy calculations. It is also important to know that 4 out of the 13 systems in this set have shown that null models, such as molecular weight and log P, also have significant enrichment power. So it is important to evaluate these null models first and to use them as a benchmark to assess the true performance of a free energy method. So in the second part of this presentation, I'm going to showcase a prospective application of FEP on a drug discovery target at MoMA Therapeutics. MoMA Therapeutics focuses on a target of protein class called molecular machines. These are proteins that generate motion through significant conformational change driven by some nucleotide hydrolysis event, such as ATP. And drugging this target class at scale has proven to be pretty challenging because of these large conformational change related to the enzymatic work cycle. So there are a couple of X-ray crystal structures available internally with resolution range in 2 to 3.5 angstrom determined for inhibitors across 5 different congeneric series. And we carried out prospective FEP calculation throughout the lead optimization process that feature a highly dynamic ATPase protein stabilized by covalent inhibitors. And FEP plus has been applied to so far about 270 compounds, and 60 compounds were made, which span a dynamic range of binding affinity of about 4 kcal per mole. And most of these compounds carry 3 R groups. Yeah, so I will talk more detail about each performance. So here shows the overall FEP plus calculated binding affinity compared with experimental data in biochemical and cellular assays. And so it is encouraging to see that FEP plus calculations achieve reasonable accuracy and rank ordering ability for both biochemical and cellular assays. Most of these compounds have predicted accuracy within 1 to 2 kcal per mole of experimental data, which are about twice as big as the prediction uncertainty and experimental uncertainty. And the RMSE are comparable to the published benchmark as well. Along the way, we also accumulated some lessons about FEP plus in terms of its strengths and weaknesses. In one example, we observed the X-ray structure in the different X-ray structures that we solved. A phenylalanine residue near the binding pocket can flip back and forth, and this motion is also important for engaging the ligand. And in the FEP simulations, we were able to observe consistently flipping motions for this phenylalanine that also account for protein-ligand interactions. In another case, we observed a tenfold potency loss when we look at a matched molecular pair of a covalently bound covalent inhibitor versus a non-covalent counterpart. And from FEP calculations, we were able to identify that a torsional strain in the R group next to the warhead have high conformational strain. This is especially problematic when the ligand is covalently bound to the protein. So it helps reveal some of the insights about binding and SAR. In other cases, there are some issues with the free energy calculations. Some of the issues are related with more substantial structural changes in protein and ligand. And in other cases where we see a overestimation of binding affinity for one compound is attributed to the pKa of a key hydrogen bond acceptor in the ligand is close to 7, which likely leads to multiple protonation state coexisting in the system. But in FEP, we only accounted for 1 protonation state. So that's something to keep in mind. Some of these application boundaries and as well as the system setup. We also examined the performance between perturbation pairs, and overall the FEP results have lower accuracy for these individual perturbation edges, which have a higher dynamic range in these delta D values than the experimental values. And some of these worst predicted perturbing edges are related to the core hopping perturbations, where we see a higher percentage of high error perturbations. We tried to extend the simulation time for sampling these to 15 nanosecond per lambda window. We were able to improve the energy convergence of these edges. However, the free energy difference between these perturbations have not significantly changed. Then we carried out more in-depth analyses by annotating each perturbation edge to the SAR that we are observing in each part of the molecule. And we found that in addition to the scaffold modifications, the lower accuracy are also associated with simultaneous changes of certain R groups, especially R1 and RR2 groups. And in a more detailed look at some of the examples, we identified a case where a double matched molecular pair mutation, we see some pretty significant non-additivity in the experimental SAR. Whereas according to FEP calculations, the non-additivity is minimal. So it wasn't able to pick out these non-additivity in this simulation. Then we carried out more in-depth look into the SAR around R1 and R2 groups, and we found in many cases they have more significant non-additivity than modifications in other parts of the molecule. And we carried out some enhanced sampling on these simulations and were able to identify that the cause of these non-additivity are likely related to the long-range correlated motion between two regions around R1 and R2 groups, which likely will need to require more enhanced sampling beyond the capability of the current FEP protocol to provide full account for this effect. So this plot shows the kind of the progress of free energy calculations over time, where the compound we made more recently are in bigger, darker circles. And we found that over the course of 10 months, FEP have guided the lead optimization process to achieve a few kcal per mole improvement in potency. And also now with deeper understanding about the success and the limitation of FEP applications, we are promoting more unbiased prioritization effort based on these FEP predictions to maximize the utility in prospective predictions. So yeah, here are some take-home summaries. And lastly, I would like to thank my numerous talented past and current coworkers. Some of you are here today that worked with me on these projects over the years and supported me along the way. And most importantly, I would like to thank all of you for your attention. And thank you.
Okay, we have time for one question. Oh, over there, the back. Walk in.
Very nice talk. When you show the prospective study of every 2 months, I noticed that the distribution in the were uniformly distributed, almost uniformly distributed. So how do you use the FEP funds to actually select the compound? Because I would imagine if you use it prospectively, you'll have more compounds that have higher predicted binding frequency than the compounds with lower binding frequency.
Yeah, that's a very good point. Yeah, yeah, that's right. Yeah, by comparing the compound we made and the ones that we have calculated in FEP, that we see still a shift in the distribution. But yeah, some of these are due to a time like delay because we're still making some of these compounds that are very well predicted at the moment, and the synthesis is a bit challenging, so we're cranking on them. Additionally, in the beginning of this perspective exercise, the chemists are more cautious about, just buying on whatever FEP is predicted to be good. They want to test both the good and bad ones in order to have a more unbiased estimate of how well FEP can pick out the good binding signals. So I think overall we were able to currently prioritize more potent compound from the predictions for synthesis.
All right, and with that, let's thank Cindy one more time and go get lunch.
Sorry, can I make a quick announcement before we go? So lunch is upstairs. If we can be back here for 1:15, we're going to be announcing the post prize.